So welcome back. In this video we're going to do some exercises with quantifiers. Okay, a very nice exercise if we have some sentence like the first one. For every integer x squared is larger 0. And then the question is, can you write this in a more mathematical way, so in a symbolic form? Okay, let's give it a try. For every, so that means we have to use the universal quantifier. So capital A, for every. And they've given us already a name of the value they want us to work with, x. And they tell us what type of is this x. So it's an integer. So an integer coming from z. Those are all integers. And what is the propositional function? X squared larger 0. Okay, so for every integer x is for every x is an integer, x squared larger 0. Okay, is this true or false, by the way? Well, at first sight you would say it's true, because x squared is also always positive. But remember, in z we also have the possibility of the value 0 itself. And 0 squared equals 0. So this complete proposition is false. Now we have at least one element for which it doesn't apply. Okay, the second one, there exists an integer x. So now we have there is the e. And we already received a name, x. The domain of x is again z, integer. And what do they want us to know about this x? Apparently that x squared equals x plus 10. So there is an integer x coming from this z, so in such a case that x squared equals x plus 10. Then the last sentence, there does not exist an integer x such that x squared larger x plus 10. So then let's first do the sentence, there is an integer x such that x squared is larger x plus 10. So let's try it. So there is an element x coming from the domain z in such a way that x squared larger x plus 10. And then they say it is not the case. So the only thing you need to do is put a not in front of it. So it's not so that we can find an x in such a way that x squared larger x plus 10. But of course, if you find, you take x for instance being 5, and 25 is larger than 15. So this complete sentence is equivalent with false, because we can't find an element such that x squared is larger x plus 10. Okay, another exercise, and this is quite common. We will do this on the exam. So we have a domain given by a set, and we have an array. And an array is just a series of elements. And we call it an array because if we look at programming languages, then we make it an array, and the name of the array is A, and with the help of an index, so 0, 1, 2, 3, 4, we can find the corresponding values. So we have a domain 0 until and including 4, and we have 5 corresponding values belonging to those index. Okay, then they have given us a property, and they say, and then we just have to assume that this is true. So this proposition is given as a truth, that for all elements, and we talk about the elements with the symbolic name I, this I comes from domain, and in this case 0 until and including 4, and they tell us that AI, so the corresponding value from the index, equals the index itself minus 2. And then the first question is, give us the elements of A0 until and including A4. Okay, let's make some space, and the other questions we'll do later. So give the elements A0 until and including A4. So, okay, let's try to start with A0. And if we look at the property, we know that A0 equals 0 minus 2. This is the corresponding value. So A0 equals minus 2. A1 would be 1, I is 1, minus 2, so that would give us minus 1. A2 will give us 2 minus 2, being 0. Okay, A3 would be 3 minus 2, would be 1, and A4 would be 4 minus 2, being 2. So we have a nice regular series starting with minus 2 and then incremented with 1 for every new index. Okay, then let's have a look at the questions. Okay, I've just put the result of the last slide on the top of this slide, and then we can look at the propositions. So, first one, for all elements coming from the universe, and then they mean, of course, universe D, AI is larger than 2. So if we look at the elements of AI, then I find 4 of them which are smaller than 2. So this is obvious false. Okay, next one, for all elements coming from the given universe, so D again, I larger 0, so we only start looking from A1. They say AI minus 1 is smaller than AI. Okay, AI minus 1, that would start from A0, is smaller than A1. A1 is smaller than A2. A2 is smaller than A3. Okay, that's good. This'll work. So that's true. Then an existential one. We can find an element from that domain in such a way that we can find an element from the same domain, so that the two elements, if we add them up, they give us 0. Okay, can we find? We only need to have one example. And then, of course, we can find plenty of examples. For instance, if we choose I being 0 and J being 4, then A0 plus A4 would be minus 2 plus 2 would be 0. So we already find one. Yeah, but we could also have the combination I is 2 and J is 2. And so then we have A2 plus A2 being 0 plus 0 equals 0. Oh, again, we found one. So, but we only need to find one, so this is true. Then the last one, for all elements I coming from that domain, for all elements J coming from that domain, and now notice there is an extra condition, they may not be the same element. So if I look at I being 0, then I have to look at all other elements, so J would then be 1, 2, 3, 4. If I check I being 1, then I have to check J being 0, 2, 3, 4, etc. So for all elements, it says that all other elements do not have the same value. Okay, let's give it a try. In fact, we need to check all of them. So let's choose I being 0. Then for all other elements, the values are not the same. Okay, for J is 1, 2, 3, 4. Indeed, they're all different. So for all J's except 0, it's different. And in fact, we don't have to check all of them, because we know that all values are different. So if I may not use the same value, then all other elements are different. So this is equivalent with true. Okay, then another exercise. So we have a domain again, and then they ask us, is the proposition there is an element coming from that domain that the element itself, so x itself, is larger 20. Okay, can you find one element in the domain which is larger 20? And then of course you would say no. So this is false. Okay, can you find the second one? Can you find the b in such a way that 2 times b is larger than 13? Yes, of course we can. True. For example, take b being 7. That would do the trick. Okay, third one. For all elements coming from that domain, I can say that 2 times I is larger 3. Okay, and then in this case, don't check all of them, but check the smallest. If the smallest work, then all the others will be bigger as well. So 2 times 2, 2 is the smallest, is already larger 3. So all the others are larger as well. So this is true. Then the last one, for all elements y coming from this domain again, 2y is smaller than 28. Okay, it's the opposite of the first one, of the third one. Now check the largest. The largest is 8, and 2 times 8 is 16. That's already smaller than 28. So all the others will be smaller as well. So, true. And on the exam you will find that with some common sense you'll get far on this exam. So just don't confuse the existential one with the universal one. So existential one, you only need to find one. Universal one, it needs to apply for all. Okay, and to make life complicated, we can also make combinations of the propositions. So, for instance, there is an element x coming from the domain D in such a way that there is an element y coming from that same domain in such a way that x, the first element, is smaller than the second element. And of course, that is true. You can take x being 4 and y being 7, and then it would work. And only one example is more than enough. Okay? For all elements x, for all elements y, x smaller y plus 1. And the universal one is always more difficult because then they all have to work. So for all elements x, then for all other elements y, x is smaller than y plus 1. Okay, let's take x being 8. And then for all elements y, 8 is smaller than y plus 1. Okay, and then you would say, of course, that is not true. Because if we choose y being 2, then 8 smaller than 3, that's complete nonsense. So if we look at the universal one, then it's more easy to show that it's false, because then you only have to find one counterexample. So this one here is false. It's not true. And one last one. Now we start with the universal one. For all elements, I can find at least one element in such a way that x plus 1 is larger than y. Okay, for all elements. So, for instance, if x is 2, then can I find a y in such a way that 2 plus 1 is larger than y? Okay, and hopefully you already see that if we choose y being the smallest one, that it will always work, because if x is 2, 3 is larger than 2. X is 3, 4 is larger than 2. And so by finding a nice example of y, we have proven that this one is true. Okay, hope you enjoyed this lesson. In the next lesson, we'll introduce some more quantifiers.